Okay, so we've been exploring this idea of charged particles experiencing forces in a magnetic field. And if I have a current carrying wire, that wire is going to experience a force inside of a magnetic field. I'm going to put these two things together, and I want us to kind of dive into the wire now. What's actually happening inside the wire? Because current, remember, is the flow of electrons in the wire, right? So charged particles are actually moving. So overall, we get this force on the wire, but what about the forces inside the wire? What about the electrons inside the wire? What's going on with those? So let's dive into the wire. Okay, so imagine this is a wire, we're zooming in, and it's in a magnetic field that's kind of going into the page. So I'm gonna put the magnetic field into the page, so that's the B field. Okay, it's going into the page, that's what those little X's mean. And this is the top of the wire. We'll say here's A, top of the wire, and the bottom of the wire is point B. So kind of imagine I've cut that wire, cross-sectioned it, and we have A on the top, B on the bottom. The edge of the wire, of course, it is wire, so it's circular. The field is going into the page. And if we imagine that there is an electron within that wire moving along, that electron's moving along inside this wire because there's a current being produced in the wire, and it too is going to actually feel the force of that magnetic field. So if we think about the force on a charged particle, we know that the force on the charged particle is QV B sine theta, and we're perpendicular here, so we're going to be at that maximum value. We're just going to have that sine of theta be 1. Now the charge is negative, right? So because Q is negative, the force on this electron is downward. Okay? So this electron feels kind of a downward force. And if we look at all the electrons moving through this wire, what ends up is that these electrons sort of collect along side B. So there's this drift of the velocity towards side B. And that means less are near side A. So I get this collection of electrons at side B. We've drifted a little bit, and we call that the drift velocity of the electron. It collects, so to speak, at side B, lesser at side A, and now what do I have? Well, this leads to a separation of charge. And what do we call that? Well, thinking back to separation of charge, that's an electric potential. And there's a potential difference here. And I get a voltage. So I get this tiny little EMF in the wire, where it's more positive kind of at the top of the wire and more negative at the bottom of the wire. I get this small little EMF, this small little voltage potential happening, which means there's an electric field inside of that wire. And so I suspected you were thinking, wait a second, these electrons are moving, right? And even though this wire's feeling a force, those electrons also have to be feeling a force because they too are charged particles in an electric field. And what does that cause? It causes this little drift of the electrons towards, in this case, the bottom half of the wire, right? Towards one side of the wire. And a small little EMF is set up inside that wire. And I just wanted to introduce you to this idea. This idea is known as the Hall effect. And that tiny little voltage, that separation voltage, we call the Hall potential. All right, so I just want to introduce you to that idea as we continue our discussion of magnetism and the interplay between electricity, static electricity, and magnetism. All right, good job.